Hello everyone, I welcome you all to Startup Academy, your online gateway to ISS exam. So today, as we have been doing in the previous lecture, we will continue with our descriptive paper of statistics, which is statistics paper 3. And we have till now we have done simple linear regression model, multiple linear regression model, and today we will do Gauss-Markov theorem. Now, Gauss-Markov assumptions are different and Gauss-Markov theorems are different. So we will today do Gauss-Markov theorem, and then after that we will do one question as we do in every lecture of the PYQs. So let us start with Gauss-Markov theorem. Now, what does Gauss-Markov theorem says? Gauss-Markov theorem says that OLSE, which is ordinary least square estimator, is the blue, which is best linear unbiased estimator. Which says that in the multiple linear regression model we have calculated OLSC, which is ordinary least square estimator beta cap, which had the value x dash x inverse x dash y. It is the best out of all the other estimators of the model. Now to prove this, firstly we know that beta cap, as we have calculated in MLR, is x dash x inverse x dash y. This is our beta cap estimator, beta cap. Now to prove that it is the best, we have to take another estimator to prove. So let us consider beta curl. Beta curl is equals to a dash y, where a dash is any constant. So beta curl is a dash y, b another estimator of our model. Beta curl a dash y is another estimator of our model. Then we can say that consider beta curl is an unbiased estimator of L dash beta. If we would have taken only beta here, then the estimator would have been the same. There would have been no change. So we have taken a linear function of beta, which is L dash beta. Now we know that estimation of beta curl is nothing but L dash beta, as we have considered in this, and we know that the value of beta curl in from the previous slide is a dash y. Substituting the values here, a dash is treated as a constant, comes out of it, and we are left with estimation of y. Here y can be written as x beta plus epsilon and L dash beta. Now this estimation, x and beta are treated as constant, estimation will go on epsilon, which is the error term, and we know that we know that estimation of epsilon is nothing but 0 from Gauss-Markov assumptions. So we are left with a dash x beta is equals to L dash beta. Now from here we can say that a dash x is equals to L dash. Let us consider this as equation number 1. A dash x is equals to L dash. Now moving on further, we will calculate the variance. Now variance of beta curl is given by variance of value of beta curl is a dash y, which can be written as a dash variance of y into a. Now again this will become a dash variance of y is nothing but sigma square in and a. If we multiply the identity matrix, there is no difference. So our variance will become sigma square a dash a. Let us consider this as equation number 2. Now again we will calculate variance of L dash beta. Now variance of L dash beta is nothing but L dash variance of beta into L. L dash variance of beta into L. Now L dash will remain as it is. We will not change since L dash here. Variance of beta, as we have calculated in multiple linear regression model, is nothing but sigma square x dash x inverse. If you don't know how to calculate this, you can see our previous video in which we have calculated the estimation and variance of beta. So sigma square x dash x inverse into L. This will be our variance. Now from the equation number 1, L dash is nothing but a dash x. So substituting here, we will get a dash x sigma square x dash x inverse x a x dash a. Because we have to take the transpose of L, so it will become x dash a. Now let us see here. When we calculate the predicted value of y, which is nothing but x beta cap. Here we can write beta cap as x dash x inverse x dash y. Now this whole value we can take it as h, which is hat matrix into y. So here also we will take sigma square outside a dash x x dash x inverse x dash a. Now this value again is the hat matrix H. We can replace it with that and we are left with sigma square a dash h a. This becomes our equation number 3. Now since we have to find the best, so we have to consider that its variance should be the least out of the two of them. So calculating variance of beta curl minus variance of L dash beta is equals to from equation 2 and 3, variance of beta curl is sigma square a dash a and variance of L dash beta is sigma square a dash h a. So this will be sigma square will take common, a dash also common, we are left with in minus h and a afterwards because we are doing this in matrix. So sigma square a dash, this I minus h will become h bar, that is bar of hat matrix and a. Now we know that h bar is semi-positive matrix, and definite. This is the property of matrices. H bar is semi-positive and definite matrix, and so A dash H bar A is in quadratic form. Hence, A dash H bar A is always greater than equal to 0. Since H bar is semi-positive and definite matrix and A dash H bar A is in quadratic form, we can conclude that A dash H A is always greater than 0. Now moving on, we can write that variance of beta curl minus variance of L dash beta should also be greater than equal to 0, because it is equal to A dash H bar A. Now taking variance of L dash beta on the right hand side, we will get variance of beta curl is greater than equal to variance of L dash beta. And this is how we prove that variance of L dash beta is less than any other estimator of the model beta curl, and hence it is blue. So hence OLSE, which is ordinary least square estimator, is always blue. Blue means best linear unbiased estimator. So this completes our theorem, Gauss-Markov theorem. So now we will do a question as we do in every lecture of the PYQ. This question behind me is of the year 2021, which says that we have been given a model yi is equals to beta naught plus beta 1 xi plus epsilon I, where I goes from 1 to n and epsilon I are IID normal 0 to sigma square, means estimation of epsilon I is 0 and variance of epsilon I is sigma square. So firstly, we have to calculate the OLSE of beta naught and beta 1, which and prove that they are the linear functions of yi. And secondly, we have to calculate the variance covariance matrix of beta naught, beta 1 and its determinant. This question is of 15 marks. So let us start solving. First part, OLSE of beta naught and beta 1. From here only, we will see that model is yi is equals to beta naught plus beta 1 xi plus epsilon I, for all I goes from 1 to n. Now yi is this. The next thing we will do is we will calculate by OLSE, ordinary least square estimation method. We will take E, which is nothing but summation I goes from 1 to n EI square. So here we can take it as E is equals to summation I goes from 1 to n yi minus beta naught minus beta 1 xi, excuse me, whole square. So again we will take two normal equations. Firstly we will differentiate with respect to beta naught and then beta 1, and we will get the OLSE of beta naught and beta 1 respectively. So taking the first normal equation, we will get minus 2 summation I goes from 1 to n yi minus beta naught minus beta 1 xi should be equal to 0, and substituting it, taking in the summation, we will get summation I goes from 1 to n yi minus n beta naught minus beta 1 summation I goes from 1 to n xi is equals to 0. Taking beta naught on one side and the rest terms on the other side, n beta naught is equals to summation I goes from 1 to n yi minus beta 1 summation I goes from 1 to n xi. Now dividing the whole equation by n, we will get beta naught cap as y bar minus beta 1 x bar. This is our OLSE of beta naught. Now moving on, now we will see that here beta naught, we can observe that we can write it beta naught as 1 upon n summation I goes from 1 to n yi minus summation I goes from 1 to n ki yi into x bar. So we can clearly see that beta naught is the what we have done in this. We can clearly see that beta naught is the function of yi. Taking the common terms out, 1 upon n summation I goes from 1 to n. Here we can write x bar. We are left with yi minus ki yi, which is nothing but yi, which is the function of yi. Now for the second equation, we will differentiate this with respect to beta 1. Now this will become minus 2 summation I goes from 1 to n yi minus beta naught minus beta 1 xi into xi is equals to 0. Now taking summation inside, we will get summation I goes from 1 to n yi minus xi summation I goes from 1 to n beta naught yi xi minus beta naught summation I goes from 1 to n xi minus beta 1 summation I goes from 1 to n xi square is equals to 0. So now opening beta naught, summation I goes from 1 to n yi xi minus y bar summation I goes from 1 to n xi plus beta 1 into x bar summation I goes from 1 to n xi minus beta 1 summation I goes from 1 to n xi square is equals to 0. Now we will take these two terms and these two terms separately. So this is I goes from 1 to n yi xi minus n x bar y bar minus beta 1 summation I goes from 1 to n xi square minus n x bar square. All of this we have done in the simple linear regression model. So if you find it confusing in any step, you can check that video of ours. So taking all the common terms on one side, we will get beta 1 cap is equals to summation I goes from 1 to n yi minus y bar into xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square. This is the OLSE of beta 1 cap. And here we can also write this as summation I goes from 1 to n yi into xi minus x bar upon summation I goes from 1 to n xi minus x bar whole square. Since y bar into summation xi minus x bar is mean deviation, which becomes 0. And from here we can conclude that beta 1 cap is linear function of yi, since only the power of yi is 1. Now moving on to the second part of the question, which says that we have to find the variance covariance matrix of beta naught and beta 1 and then find its determinant. So variance covariance matrix of beta naught and beta 1. This can be written as variance of beta naught into covariance of beta naught and beta 1, covariance of beta 1 and beta naught into variance of beta 1. Since we have calculated variance of beta naught and beta 1, so I am putting directly the values. Variance of beta naught is nothing else but sigma square 1 upon n plus x bar square upon sxx. This is the variance of beta naught, and variance of beta 1 cap is nothing but sigma square upon sxx. Now we have to find the covariance of beta naught and beta 1. So covariance of beta naught cap and beta 1 cap can be written as covariance of x bar minus n y bar minus beta 1 cap x bar into beta 1 cap, which again can be written as covariance of y bar and beta 1 cap minus x bar variance of beta 1 cap. Now here covariance of y bar and beta 1 cap is covariance of 1 upon n summation I goes from 1 to n yi into summation I goes from 1 to n ki yi. So this will, taking common terms outside, we will get 1 upon n summation I goes from 1 to n ki into variance of yi. Now variance of yi, we all know that it's sigma square upon n summation I goes from 1 to n ki, which is nothing but 0. So this value becomes 0 and this value. So we are left with covariance of beta naught cap and beta 1 cap is equals to minus x bar variance of beta 1 cap, which is minus x bar upon sxx. From here, now putting all these values in variance covariance matrix, we will get variance covariance matrix is equals to variance of beta naught, which is sigma square 1 upon n plus x bar square sxx. Then again, this covariance become minus x bar upon sxx. Then this also becomes x minus x bar upon sxx, and this becomes sigma square upon sxx. It will also be sigma square. So this is our variance covariance matrix. Now we have to find the determinant of this. Determinant of this becomes determinant of this becomes sigma square 1 upon n plus x bar square upon sxx into sigma square upon sxx minus x bar sigma square upon sxx into minus x bar sigma square upon sxx. The determinant is cross multiplication of these two and these two. The left and right minus this right and left. So after, on multiplying, we will get d equal to sigma raised to the power 4 upon sxx 1 upon n plus x bar square upon sxx minus sigma raised to the power 4 x bar raised square upon sxx square. So on multiplying this inside, sigma raised to the power 4 sxx into 1 by n plus sigma raised to the power 4 x bar square upon sxx whole square minus sigma raised to the power 4 x bar square upon sxx whole square. So these two terms are common, and with negative and positive sign these two gets cancelled, and we are left with determinant is equals to sigma raised to the power 4 upon n sxx. This is our determinant, and this completes our question. So I hope you guys understood all the things that we have done. If you didn't understand any concept, then you can put the comment, and we will answer the relevant comments. And you still have any doubts, you can see our previous lectures before moving to this video. Thank you everyone.